Hello all. Today we're going to be studying to get ready for the Unit 4 exam on electricity and magnetism. All right, let's start question number 1. We have two metal spheres having charges of 4 by 10 to the negative 6 and 2 by 10 to the negative 5 Coulomb, respectively, and they're brought into contact and then separated. And after separation, the charge on each sphere would be. So the way I solve questions like this is I will just take the two stated charges. I understand that charges can migrate when conducting spheres touch, so I will just add those two charges together and divide by 2. So an interesting note is that when you're adding scientific notation numbers, you don't use the same tricks with the exponents, meaning they don't sum on the top. So you actually, what I do is I actually put these guys in parentheses and I add them together in my calculator. And I was doing this on my phone and it gave me this answer. But with scientific notation, we can adjust that. So if I take the decimal 1, 2, 3, 4, 5 places to the right, then that's like saying 1.2 times 10 to the negative 5 coulombs, which would be my final answer. All right, next question. A subatomic particle could have a charge of one of these. The way we solve that is we look at the charge of one subatomic particle, and we find a value in the answer choices, which is a multiple of that charge. On the front page of my reference table, I know that an elementary charge is 1.6 by 10 to the negative 19 coulombs. So I'm leaning towards choice 3 as my answer because I can see that it's just 2 elementary charges. Number 3. The diagram below shows two small metal spheres, and they're labeled A and B. And each sphere possesses a net charge of 4 by 10 to the negative 6. So those are both labeled. And they're separated by a distance of 1 meter. That's going to be the radius. And we want to know the combination of charged spheres and separation distances, which would produce an equal force. So there's a way to do this where you would do, 5 total different calculations. But I think it's better to treat this holistically by looking at the equation for electrostatic force. So if we treat this scenario as the normal scenario, and we also generalize it to being this equation, we can look at these values, think of them as being either half of the original or, twice the original. And then we can also see how these radii compare as well. So as I was looking through the answer choices, I noticed that choice 4 was particularly appealing for more than one reason. I know that 8 by 10 to the 6 is twice of 4 by 10 to the 6, and I see that twice here. And I also know that 2 meters is twice 1, so it's really easy to see how I would manipulate this equation. I suggest that we would simply double the Q, and double this Q, and double this R. Now, doubling these two Q's up here is going to give you an overall effect of 4, so that's 4 Fe. But doubling the R in the denominator is also going to be a double square, and it's going to give you an overall value of 1/4. So then you're going to have the 1/4 here. And then, of course, 1/4 times 4 is actually 1. So when they ask me which of these is going to produce the same magnitude of electrostatic force, then my best answer is choice 4. In number 4, we have a negatively charged sphere and a point P, and we are being asked which vector best represents the direction of the electric field at point P. So remember, electric fields are defined based on a positive test charge. So a positive charge would undoubtedly feel an attractive force if it were near this negative sphere. So we would see these lines which are being drawn tangent to the surface like that. Now if it passed through point P, it would look exactly like this one. So my best answer is choice 1. Which graph best represents the relationship between the magnitude of the electric field strength E around a point charge in the distance, r, from the point charge. So consider a positive conducting sphere and the field that would surround it. Remember, this is based on a positive test charge. So you would see lines traveling outwards from the sphere, not curving because they're not curving towards anything. They're just trying to go straight away from the positive sphere. All right, now I want you to notice that the field lines are closer together at the base or near the sphere, and they're more spread out as the farther you get away. This is because of the inverse square relationship between electrostatic force and distance. And using that, we can imagine that the electric field is certainly weaker. The strength of the electric field is weaker up here, where you have fewer electric field lines, and stronger down here. So I think that we can take a holistic approach to answering this question and go with choice 4. So 6 and 7 are both based on this diagram. I'm going to read both questions before I answer either one. So we have some parallel plates. This is the electric field strength. And here's point P, positive, negative. One question wants us to calculate the force exerted on the electron by the field. And number 7, it wants us to sketch the field lines. I'll do 7 first since that's easier. Remember, the field lines are defined as the direction a positive test charge would feel its force. So the positive test charge would feel repelled by the positive plate. So I'm going to draw my 5 field lines going away from the positive and towards the negative. Okay, so that's done, and let's do number 6. They're asking us about point P, and ultimately they want me to find the magnitude of the force exerted by the electric field. A convenient equation to use here is also from your reference table, and it's E equals Fe over Q. We are looking for Fe, so when I rearrange that to be proper, I'm going to see that Fe is EQ. Now the electric field strength was stated in the question as 2.0 by 10 to the third, and the charge of an electron is the same as the charge of an elementary charge, which is going to be 1.6 times 10 to the negative 19 coulombs. So I'm going to combine these two items. The 2 and the 1.6 are going to multiply to give me 3.2 times 10 to the, and the 10 to the third and the 10 to the negative 19 are going to combine to give me 10 to the negative 16. So there's my 3.2 by 10 to the negative 16 newtons, since this is a force. And that's my final answer. All right, number 8. If 1 joule of work is required to move 1 coulomb of charge between 2 points in an electric field, the potential difference between the 2 points would be which of the following? So since V is W over Q, an equation I borrowed from the reference table, and work is stated as 1 joule, whereas the Q or coulombs is stated as 1 coulomb, then I know that the voltage here has got to be 1 volt. Now in scientific notation, it would look like that. In number 9, the current through a light bulb is 2 amperes. How many coulombs of electric charge pass through the light bulb in 1 minute? So one thing that I know that we should probably go ahead and get out of the way right now is that 1 minute is actually 60 seconds. So we'll deal with that that way. And we're also going to use a different kind of an equation that includes current and time and charge. It's actually the first equation you ever would have received about current, and it says I is delta Q over T. So we are, in fact, looking for Q. So Q is going to be equal to IT, or current times time. The current was listed as 2 amps, and the time is 60 seconds, which means that the total charge here is going to be 120 coulombs, or choice 3. Okay, What? No. All right, number 10. A manufacturer recommends that the longer the extension cord used with an electric drill, the thicker the cord should be. This recommendation is made because the resistance of a wire varies. So here's the equation that they're about to reference. Rho is called resistivity, and it depends on the material itself. Like, is it copper, is it gold, is it silver, and so on. So we're going to ignore that for this question, but they do ask us about the relationship between resistance and length. Also resistance and area. Area and resistance have an inverse relationship, but resistance and length have a direct relationship. So the best answer here is that resistance varies directly with length and inversely with cross-sectional area. If the diameter of a wire were to be decreased, what would happen to its resistance? So essentially we're asking you, if you make the cross-sectional area smaller, what happens to resistance? So the smaller the diameter, the smaller the area, and the smaller the area becomes, the larger the resistance becomes. So the resistance would increase. Let's say we have this particular wire with that particular resistance, and let's decide what the wire could be made of. So remember that the makeup of the wire is going to be most easily described using rho. So let's solve for rho now. Using inverse operations, I'm going to have to divide both sides by L and multiply both sides by A. So rho is going to be RA over L. The resistance is 0.125. The cross-sectional area is 8.23 by 10 to the negative 6 square meters, and the length is 0.686 meters. So I just ran that calculation, and I got 1.50 times 10 to the negative 6, and I'm on my reference table looking to compare it to a resistivity for some substance to match it to, and I can't get it to match to anything. However, I do see that it looks really similar to nichrome. It's just that nichrome is listed as 150 by 10 to the negative 8 as its resistivity. And the really cool thing about this is that those are actually the same answer. Both are the same. It's just a difference in the way they appear because the nichrome is listed with an exponent of 10 to the negative 8, whereas our answer was proper scientific notation, and that would have been 10 to the negative 6. So my final answer is definitely nichrome, and for the reasons highlighted in blue. For number 13, we have a 6 ohm resistor that obeys Ohm's law, and it's connected to a source of variable potential difference. When the applied voltage is decreased from 12 to 6, what would happen to the current passing through the resistor? So voltage is the reason why a current would want to flow. You guys probably have heard me make an analogy about the difference between a lake and a river is gravity. And the stronger that gravity difference is, the stronger the lake will flow into a river. So if I'm decreasing the voltage to a voltage of about half or exactly half, I'm going to expect the current to also decrease to 1/2 of its original amount. So I'm going to go with 3 as my answer. All right, now we're looking at a graph of voltage versus current, and the slope, of course, would be resistance, because R is V over I. And this is a restatement of Ohm's law, which we could also think of as V equals IR. So they want to know during which interval in the graph does the resistor obey Ohm's law. So Ohm's law states that when voltage increases, then current also increases, and that's because the resistance is going to be staying constant, being based on other things. So there's a direct relationship between V and I. The more voltage, the more current. And the only part of this graph that actually shows a direct relationship is interval BC. So I think this is an easy one to answer for me. I would say 2, BC. In number 15, we're asked for the resistance at R3. So this is a series circuit, and I'm checking out the resistance equation for series circuit, and it looks like this. So I am going to use that equation when I end up solving, but I know the value of R1, it's 4, and I know the value of R2, which is 6. I don't know the value of R3, which means I'm going to have to know the value for REQ. There is another way to find that, and that's using Ohm's law. Remember, V is IR, but we'll do it for REQ, meaning for the equivalent resistance of the whole circuit. So REQ is going to be V over I. The voltage of this entire circuit is 24, and the current of this circuit is 2, which means that the equivalent resistance must be 12 ohms. So 12 is equal to 4 plus 6 plus R, and that means that R3 has to be 2 ohms, because 2 plus 6 plus 4 is 12. In number 16, a 10 ohm resistor and a 20 ohm resistor are connected in series to a voltage source. When the current through the 10 ohm resistor is 2 amps, what is the current through the 20 ohm resistor? All right, so I just included a diagram because that really helps me understand questions like this. It did say there was a 10 ohm and a 20 ohm resistor in series with the voltage source, and that the current through the 10 ohm resistor was 2 amps. So I put an ammeter here showing 2 amps of current. So this is connected, ammeters are connected in series with the resistor they're measuring, so this is the correct arrangement. But there's something else, which is that in a series circuit, all of the currents are equal. So according to this equation, the current of 2 amps at the 10 ohm resistor is going to be true anywhere in the circuit. So that means you're going to have a current of 2 amps even at the 20 ohm resistor. Okay, number 17. In the circuit shown below, voltmeter V2 reads 80 volts. And we want to know the voltmeter reading of V1. According to Ohm's law, R is V over I, and that would mean that I is V over R. I'm going to put this to use because for a series circuit, all of the I's are equal, meaning that the current that passes through this resistor is equal to the current passing through this resistor. That's just a rule because there's only one pathway for these guys. So they're both going to be equal in current, which means they'll also be equal in terms of their V over R. So essentially, I can solve this one as a proportion between the V over R's. So let's go ahead and do it that way. Let's say that V1 over 40 is equal to 80 over 20. This is all data from the question. So if that's true, then the answer must be 160. So for the next question, we have a circuit connected in parallel, and it has a 10 ohm resistor, a 15 ohm resistor, and a 20 ohm resistor. We're asked to find the equivalent resistance. The reference table gives us this equation. So it's basically set up for us. I'm just going to plug in the values that I know. So of course you could do this in your calculator, but I'm going to do it the old-fashioned way. Each one of these fractions before they're added needs to have a common denominator. And the one number that they all have in common, their lowest common denominator, would be 60. So I'm going to adjust each fraction to be out of 60. So the first fraction got multiplied by 6, the second multiplied by 4, and the third multiplied by 3. 6 plus 4 is 10, plus 3 is 13. So 1 over REQ is 13 over 60. That also means that REQ is 60 over 13, and I will use my trusty calculator to find the decimal equivalent. And I got 4.62 ohms, so my best answer is choice 3. For number 19, it seems like we have a parallel circuit with 2 resistors and 3 ammeters, and they want to know the reading on ammeter A1, which is right here. Your reference table tells you that for parallel circuits, the currents will add up to equal, the currents on the branches add up to equal the current for the entire circuit. So the entire circuit's current is this I, which is going to be 10 amps. And I1 is going to be for resistor 1 or ammeter 1. We don't know the value for that, so I'll leave that as I1. But I2 is going to be resistor 2 or ammeter 2, and it's telling us that it has 4 amps of current in it. There is no third branch. So 10 is I plus 4. I1 must be 6 amps, and my choice is 2. All right, so for this next question, we have a nice parallel circuit with 4 branches and a 12-volt battery, so we're going to have a 12-volt drop at each resistor. And we're asked how much power is dissipated in the 36-ohm resistor. So with only the information to go by voltage and resistance, I need to find an equation that can also give me power. And on my reference table in the electricity section, I have my eyes set on this one, P equals V squared over R. The V squared is the voltage or the potential drop, and we are focusing in on the 36 ohm resistor here, but it's going to have a potential drop which is equal to all the others and equal to the battery. So I'm going to go ahead and use the that 12 volts as my potential drop. So I'm going to go with 12 squared, and the resistance, of course, is 36 in this case. 12 squared over 36 is 144 over 36, which is going to give us 4 watts of power being dissipated across this resistor. 21. We have a nice series circuit, and they want to know the rate at which electrical energy is expended in a 16-volt 4-ohm circuit. Now, the rate at which energy is expended is code for power. So we are looking for power again, and again, we only have information of V and R. So let's go ahead and use that same equation, V squared over R. The voltage drop for this circuit is going to be 16 squared, of course, and the resistance is going to be the equivalent resistance for the entire circuit, which, since this is in series, it's going to be 8 ohms of resistance. So my calculation got me 32 watts as the answer, or choice 3. All right, so for the next question, I'm going to label variables as I go to help me choose an equation. So a 4.5 volt, so obviously that's your voltage, personal stereo uses 1950 joules of energy. So that's going to be the work that's being done in 1 hour. This is going to be time, but just for the record, an hour is 3,600 seconds, and we will want to use the seconds value. What's the electrical resistance, or R, of this personal stereo? So we need an equation that can relate V, W, T, and R. So the equation I found in the reference table is W equals V squared T over R. Okay, we're looking for R, so I'm going to multiply by R on both sides just to eliminate it from the denominator. Cancels on the right. And then I have R, W is V squared over T, but I'm still looking for R, so let's divide both sides by W, put it right down there in the denominator. Cancels on the left, and my new transformed equation says that R is V squared T over W. The V we already knew from earlier is 4.5, but make sure that that gets squared. The T is going to be 3,600, as I had pointed out, and the W, or the work being done, is 1950 joules. So I just ran the calculation, and I got 37.4 ohms as my electrical resistance, so choice 3 is my answer. And in 23, it says that we have an electron accelerated from rest through a potential difference of 200 volts, and they want to know how much work is being done on that. So I just looked at the answer choices and noticed they were all in electron volts, which reminded me that 1 electron volt is equal to 1 electron being pushed through 1 volt of potential difference. So essentially what they're asking me is how much work or how many electron volts are needed to move 1 electron through 200 volts. So I think it stands for logic here that the answer would be 200 electron volts. which is choice 4, and also my final answer. So for 24, you guys have seen this one before, but they want to know where the magnetic field would be strongest. It's going to be strongest here where the flux line density is highest. So C, final answer. In 25, it's also about magnetic fields, but they want to know what the magnetic field might look like near a bar magnet. So there are a few rules for magnetic field lines. The first one is that they can never intersect. The second is that they travel from north to south outside the bar magnet. The third is that it's south to north inside the bar magnet. And the fourth is that they always form closed loops. And the only diagram that meets all of those requirements is choice 2. All right, and that concludes our review for the Unit 4 exam on electricity and magnetism. I hope you enjoyed, and I hope that you also will do your own studying and get yourself super prepared. Thanks for watching, and have a good night.